As you all know, I tend to get very excited and enthusiastic about physics. And no surprise, this lab is one of those labs that I am extremely excited about. I think it's actually probably the coolest lab that I've ever designed. And the reason is because we're taking this process that an actual piece of life evolved, this gannet bird, right, who is able to use the law of conservation of energy in order to help it hunt its prey, its fish inside the water, right? So what this bird does is it uses the fact that up high it has lots of potential energy, and then as it dives, that potential energy is going to be turned into kinetic energy so that it can penetrate the water deep enough to snatch its fish, right? Sorry, but that's pretty freaking cool. And the fact that we can use tracking software to prove this, as we will in this lab, is pretty neat. Okay, now, because this one's a little bit more technical, I want to make sure I'm very clear about how to do it. So here is the process, right? First things first is you have to upload or import the bird's video, which is in the lab assignment in the week 9 module. Okay, so just go to there and download birds onto your computer, and then you can go over here to import, click AVI because it's an AVI file, and then just select the birds that you've downloaded on your computer. Okay, after that, the first step of this whole process is we need to find a way to calibrate how many meters are in each pixel in this video. Okay, now there's a very convenient way to do this. We know that these birds are about 1 meter long. So if we can find the length of this bird in pixels, we know the number of pixels per meter, which means we can just invert that to find the number of meters per pixel. All right, so how do we find the length of this? Well, we go back to plugins, we go to tracking, we go to manual tracking over here, and we just add a track, okay? With that, we don't worry about any of the parameters now, we're just adding a track. And now we're going to just bring the bird into view here, right? And we're going to hit the very beginning of the bird, boom, and it gives us the pixels of where the bird's located right there, right? It gives us those pixels, right? And then we're going to do now the very tip of the bird, boom, and now it gives us the pixels for where that bird is there now, right? Cool, cool. And it also gives us velocity, but it's not calibrated yet, so that's not the correct velocity. But if we use the distance formula between these 2 points, we can find how many pixels are in 1 meter. And after we find out how many pixels are in 1 meter, we can easily find out how many meters are in 1 pixel just by inverting it, right? So not to ruin the ending, but you will find out that your XY calibration is going to be about 0.01 meters per pixel. In other words, about a centimeter for every pixel. Now notice the units here are micrometers and nanometers. Just pick unit, because then if you pick unit, you can say that the unit is whatever you want it to be, right? So I want meters, so I'm going to pick unit and just call this meters. 0.01 meters per pixel. Okay. We also have to make sure we do the time interval. So just like last time, this is 60 frames per second. So if we divide 1 by 60, we can find out how many seconds there are per frame. That ends up being 0.0167 seconds for every frame. Okay? Now we're all good. We're all good, right? We want to end the track we just started and add a new track. Okay? Click show parameters, make sure we're exactly where we were before. Okay? X out of our old thing. And now we want to start right away when we see the bird enter the screen, right? And we're going to track the motion of this bird and its velocities all the way until he splashes into the water now. So let's click on the tip here. Boom. Okay. This C6 is, by the way, the velocity. It's not naming it velocity right now, but it is, okay? Notice that it says -1. That's because we only have 1 point so far. You need a change in distance to get a velocity. Since there's no change in distance yet, it just gives you garbage, all right? So let's keep tracking it and see what happens. And I always want to use the same spot every time, right? Same exact spot because that's the best way to stay consistent. You did the same thing with the amoeba back when you all were doing the the lab in week 2 and 3. Okay, now you're not seeing the velocity. Remember, this is a velocity column. You're not seeing the velocity change too much, but it's slightly creeping up. Like the averages are creeping up, right? And that is what we should expect. Keep on tracking it. Keep on tracking it all the way until it crashes into the water. Okay, so now here's what we can do. We can take the average of the first 3, right? Take that average, find out what that is. Take the average of the last 3. The average of the first 3 is the initial velocity, and the average of the last 3 is the final velocity. And you're going to find out 17 plus 16 plus 20 divided by 3 is much smaller than 20 plus 24 plus 18 divided by 3. So you're going to see this velocity did genuinely increase. This bird got faster as it felt, right? And we're going to compare that to what we should expect to get using conservation of energy purely theoretically using the equations, right? Okay. Now, the other thing that we have to make sure that we do here is in order to find to solve the conservation of energy equations, we need to find out the initial height of the bird. So the initial height of the bird, you're again going to use the distance formula. So what was our first point? Well, it was 1140 by 92, right? And then we want to use the last point just as it crashed into the water. If we use the distance formula between this point and this point, we get the height in pixels of the bird, right? And then to turn that into meters, we just got to use the meter conversion that we found at the very beginning, okay? And it's, as far as the technical aspects of this, that's it. That's how this works. You should expect to get velocities in this region of roughly 15 to 20 into the early 20s meters per second. If you're not getting that, I would close out Fiji and open it back up and put the parameters in again and see if you're getting something closer. But that's about it. The rest of the instructions are very clearly laid out in the lab. I would like to think. But if you have any questions, you can of course reach out to me and ask as well, or ask each other using our Discord channel. All right, good luck. And let's see if we can prove that conservation of energy is real and that it is used by the gannet bird in order to hunt its prey.